Let's try this example number 6. Find a power series representation for ln of 1 plus x and its radius of convergence. For all these problems, the main concept is that um, if you have a original function f of x and its radius of convergence is r, then the derived function and the integrated function will also have the radius of convergence r. That the derivative function can be represented by taking the derivative of each term of the original function. Then the integral function can be written by taking the integral of each term of the original function. That is the whole point of this. And then geometric series is the handy one for us. It's very helpful to use that representation. So we want to think that ln of 1 plus x, how we can get from by either differentiating or by integrating um, a geometric series. So we notice that ln of 1 plus x can be obtained by integrating 1 over 1 plus x. Right? What is ln of 1 plus x? It can be written as integral of 1 over 1 plus x. So which can be written as 1 over 1 minus of minus x dx. So if I expand that, ln of 1 plus x, so integral of, so this now becomes a box kind that we discussed earlier. So it is 1 minus x plus x square minus x cube, then it alternates sign. Then we are going to integrate that with respect to x. So if I integrate each term, I get x minus x square over 2 plus x cube over 3 minus x to the power 4 over 4. Alternate sign, then we should not forget to add the constant of integration. This is kind of an identity. Now we want to find out the constant c. So you substitute any value, we will particularly choose x equal to 0 into 1. So we get ln of 1 plus 0 equal to all the terms on the right hand side involve x. All of them will become 0 except c. So c equal to ln 1 equal to 0. So substitute this value of c equal to 0 into this relation 1, equation 1, we get um, ln of 1 plus x equal to x minus x square over 2 plus x cube over 3 minus x to the power 4 over 4. If we write that in the sigma notation, it will become sigma negative 1 to the power n minus 1 x to the power n over n varying from 1 through infinity. Where does it converge? It converges only wherever the original series is convergent. When I say original, it came by integrating, ln of 1 plus x came by integrating 1 over 1 plus x. So that is a geometric series with common ratio less than 1. Negative x is actually the common ratio, so absolute value of that less than 1. So what is the radius of convergence of this new series, ln of 1 plus x? The radius of convergence is same as the radius of convergence of the original function, which is equal to 1. Let's try example 7. Find a power series representation for f of x equal to tan inverse of x. So as we said earlier, the whole idea is always we need to recognize the representation of this function in terms of geometric series that we got before. So we want to think tan inverse of x as integral or derivative of um, 1 over 1 plus or minus something. So tan inverse of x, we know, is actually integral of 1 over 1 plus x square. Why? What do you know about derivative of tan inverse of x? Derivative of tan inverse of x is 1 over 1 plus x square. So if you integrate the right hand side, you have to get tan inverse of x. Antiderivative of 1 over 1 plus x square is inverse tan x. So now, obviously, this expression looks like geometry. Why? It can be written as integral of 1 over 1 minus of minus x square dx. So this is the common ratio part in the geometric series. So expanding this, you can write inverse tan x equal to integral of 1, then it becomes minus x square plus minus x square the whole square. So that will be x to the power 4. Then minus x to the power 6. So it alternates sign like this. So if you integrate everything, you're going to get x minus x cube over 3 plus x to the power 5 over 5 minus x to the power 7 over 7, etc. Don't forget the constant of integration, that is tan inverse x. Step 2 is to evaluate, because we will call this one as step 1. Then if find the constant, find the constant c. So let's substitute x equal to 0 into the identity 1. So tan inverse of 0, which is 0, equal to 0 minus 0 cube over 3 plus 0 to the power 5 over 5. Every term has x in it, so everything will become 0. So ultimately showing that c equal to 0. Substituting this into 1, we get tan inverse or inverse tan of x minus x cube over 3 plus x to the power 5 over 5 minus x to the power 7 over 7 and so on. So it alternates sign. Also we notice that the exponents of x are only 1, 3, 5, 7 and so on. They are all odd numbers. Whatever the exponent is, that is the same as the denominator as well. Because the terms are alternatively positive and negative, so you have to introduce the negative 1 to the power n, and then it is x to the power. An odd number is always represented as an even plus 1 divided by even plus 1. So you can always make adjustments how you want to write this n varying 0 to 1 or 1 through infinity. If you are moving n as 1 through infinity, then you have to make adjustments on the exponents inside sigma. So right now we have represented the series in terms of sigma varying from 0 through infinity. And what is the radius of convergence for this? The radius of convergence, that is step 3. Radius of convergence is same as the radius of convergence of the geometric series involved in this. So it is r equal to 1. Radius of convergence would be equal to 1 for this bar series. So there are some suggested problems. In my section videos, I have done problem number 4, 5, and 15. Please refer to the section videos. For some of the problems in the suggested exercise. Hope these videos help.